In this video, we are going to find volume of the solid region bounded between the following surfaces. The first one is rho equal to 2. This is equation of a sphere of radius 2 with center at origin in spherical coordinates. The second one is rho equal to cos phi, and the third one is z greater than equal to 0. Now the third one is collection of all the points in the xy plane and all the points which lie on the positive side of z axis. Okay, and the intersection of these two surfaces is this hemisphere of radius 2 lying on the positive side of the z-axis. Okay, so now to find the volume or the solid region bounded by all three surfaces, we need to figure out what this surface represents. So let's simplify it. Rho is equal to cos phi. We multiply both sides of this equation by rho. We get rho square equal to rho cos phi. Now rho cos phi is equal to z in spherical coordinates, and rho square is x square plus y square plus z square, distance of the point from the origin. Okay, now we bring z to the other side and we can see that this represents a sphere whose center is 0, 0, 1 by 2 and radius is 1 by 2. So basically this surface is this sphere whose center lies along z-axis at 0.00 and half, with value of z is half, and radius of this sphere is also half. Okay, so what's a region bounded by these three surfaces? It's this region inside the hemisphere, excluding the region inside the smaller sphere, and we want to find volume of this region. Okay, so let's set up the triple integral to find the volume. So volume formula in spherical coordinate is given by triple integral of the Jacobian multiplied with d rho, d phi, d theta. So this is the order of integration we are choosing for to find volume in this case. We can choose some different order as well. Now what is the Jacobian in spherical coordinate? The Jacobian is given by rho square sine phi. So no matter what order of integration we are going to choose, the Jacobian in spherical coordinate is going to remain constant, and it's rho square sine phi. Now to integrate and find the volume, we need to find the limit of integration with respect to each one of these variables. So let's start with rho. To find limit of integration with respect to rho, we need to fix phi and theta. So let's understand the meaning of keeping phi and theta fixed. Now in spherical coordinates, phi is this angle. If P is the point, then we join the point P to the origin and to make this ray, and we measure its angle with the z-axis. So phi is measure of this angle this ray makes with the z-axis. Okay, so if z is fixed, then what do we get? We get this hollow cone. So phi fixed means we are on the surface of this cone. Now what's the meaning of keeping theta fixed? Theta is this angle. Say if P is any point, we take its projection in the xy plane and we join it to the origin and we measure this angle this ray makes with the x-axis. So this is the third parameter, theta in spherical coordinates. Okay, so what happens when we fixed theta? We get this plane in the xyz plane which lies along z-axis and which is perpendicular to the xy plane. So all the points lying on this plane have theta fixed. Okay, mean when we fix both phi and theta, so that means we have to consider intersection of this hollow cone with this plane. So let's see what happens. Intersection of this cone and this plane is this ray. So along this ray, both phi, the angle this ray makes with the z-axis, is fixed, and the angle, the projection of every point on this plane makes with the x-axis is also fixed. That's why keeping theta and phi fixed, we get this ray. Okay, so now to find the limits of integration with respect to rho, what we do is we start from the origin and we draw this ray. We find out this point, value of rho at this point where this ray enters the region of our integration, the region bounded region, and we find value of rho at this point where this ray leaves the region. Okay, so what is value of rho where this ray enters the region? So here this point lies on the surface of the smaller sphere. So what's the value of rho on the surface of this sphere? Rho is equal to cos phi. So therefore the lower limit of integration with respect to rho is going to be cos phi. And what's the upper limit? The upper limit is always constant and it's equal to rho equal to 2, because every row we draw starting from origin through this region of integration, it will always leave the region of integration through this surface whose equation is rho equal to 2. So the upper limit for rho will be 2 and the lower limit is cos phi, because every ray which passes through this region will enter the region of integration through this curve whose equation is rho equal to cos phi. Now you can also say, okay, this ray we have drawn, it enters the region at 0 because this point lies on both the plane and this sphere. But as soon as it enters, it leaves the region, right? So, but we want to be able to cover this point. It lies on intersection of all these three surfaces. So we don't have to worry about that because we can draw another ray, this ray, which will start from this point, lie inside the region of integration, and every point along this ray is inside the region of integration, and including this point, origin. So this point is included when we change limit of integration for phi, and phi is equal to 90 degree. Okay, so every point along inside this region is covered for some ray. Okay, so now we have our limit of integration with respect to rho. Lower limit is cos phi and upper limit is 2. So now we move on to the next variable phi. So to find limit of integration with respect to phi, we fix theta. So what happens when we fix theta? If theta is fixed, we are on this plane, right? So on this plane, phi can vary, right? For if we draw any ray on this through this plane, phi can vary, right? For each one of these rays, they are making a different angle with the z. So phi will vary, but theta is going to remain fixed. Okay, so to find limit of integration with respect to phi, what we do is we pick this ray and we drag it to the z-axis. So now this ray aligns with this axis where value of phi is 0. And as we move it on this plane where theta is fixed, we will cover this patch, this area inside the bounded region until we hit this line segment. So this is the last ray we will get, which will lie inside the region of integration. And we get it when phi is equal to 90 degree. So if we change phi from 0 to 90 degree, we are going to cover this patch inside the region of integration. Okay, so the limit of integration with respect to phi are going to change from 0 to pi by 2. Now to find limit of integration with respect to theta, let's pick up this patch. Now we have already covered, so far we have covered this region, this patch inside the region of integration. Now we want to find limit of theta, so that when we change theta, because for this patch theta is fixed, so when we change theta, that means we'll be rotating this region around the z-axis. We want to be able to cover the whole volume inside this solid. So what should be the value of theta or limits of theta to make sure when we rotate it around z-axis, we cover the whole volume? Now it's clear that the limit of theta should be from 0 to 2 pi. We need to rotate this patch around z-axis 1 to be able to cover the whole volume. Now there is another way to look at it. We can find its projection in the xy plane. We get this ray, and we need to rotate this ray around z-axis once. That means we need to change theta from 0 to 2 pi to be able to cover this whole shadow. And once we do that, we would have covered the whole region of integration. So the limit of integration with respect to theta would be 0 to 2 pi. So that will give us the volume of this region.